So this is topic 2 in our application section, and I think it would be fair to say that the application section is going to either frustrate you or you'll love this section. I think most kids fall into one of the two categories. It really depends on how well you like to solve word problems, because that's what we're going. We're now going to try to take the information that we've learned, basically how to find derivatives and what they mean, and we're going to try to apply them to a context. And as I was saying in the previous lesson, the terms that I like to use with my classes are, I'd like for you to appreciate this matters to someone somewhere. Now, it may not be you. This may not ever apply to your life or your field, but I want to try to show you how this is useful in chemistry or biology or engineering or accounting, but that there is a purpose to derivatives. We're not just doing this just for fun, although some people do find this enjoyable. But hopefully you'll agree with me after watching these next couple of videos that derivatives can be used for things. They are useful. So yeah, that's our goal, is to now work on kind of our word problems. I think what you'll discover is that the actual calculus part is very simple. Now that we've learned how to take derivatives, you're usually just taking derivatives of polynomial functions, maybe a really basic trig function, but the derivative is not a challenging function, but it's the context and knowing what to do where that kids usually find frustrating. So these next 2 or 3 lessons kind of go together in a group, and then the last thing we're going to do after this is work on something called curve sketching. So anyways, let's get into these notes here. I need to remind you what a derivative is. And but before I get to that, let's just draw a quick graph here, right? The whole point of a graph is, let's say that you have a graph of, I have a good idea here. This is how much daylight there is, number of hours of daylight there is, based on the day of the year. Day of the year. And what you might discover then, if you plot something like this, is if this was, say, let's go January, February, March, April, May, June, July, August, September, October, November, December. There you go. In terms of daylight, there's not a lot of daylight in January. But in February, there's more. And in March, there's even more. And April, there's even more. And some of you guys will probably recognize it the same way I do. It gets light out at 6 in the morning now. Like it's gorgeous out. And so there's even more daylight in May, but this pattern does not keep going, because in June it starts to slow down again, and you get the most daylight in a day in June, because then on June 21st or whenever it is the solstice, then it starts slowing back down again in July and August and September, and then all of a sudden you hit that ugly time in October and November and December where you're back to not having a whole lot, and there's like a graph behind this, and hopefully you kind of get what sort of graph this is going to be. This is a trigonometric curve. This is either a sine or a cosine graph, depending on how you manipulate it. And so one of the things that we may want to do then is calculate the slope. And the slope of this function would be like how much change there is in hours of daylight per day. And for example, this is a really key point right here, the very, very peak, because this is where there's a slope of 0. We give a special name to those. These are known as the solstices, where it's the longest or the shortest day of the year, because you don't gain any more or lose any more sunlight per day. Whereas there's another spot right here, which we're going to learn about more as we go through the unit, but there's a spot right here in March, or in, when's the other one? September, I believe, where these are known as the equinoxes, where you have an equal amount of sunlight as you have night light. That didn't make sense. You have an equal day to equal night. It's basically the same. It's the midpoint, if that makes sense. And one of the reasons why is that at this point in the year, your slope is the greatest. If I were to calculate the slope at this point right here, the amount of change from a day-to-day basis is the most. You can see this in Canada. If you were to compare sunrise in June, sunrise is going to be at like 5:15 one day, and the next day it'll be at 5:16, and the next day it'll be at 5:17, and sunrise is always around the same time. But in March and April and May, when I'm making this video right now, the amount of change you have on a daily basis is pretty big, to the point where, like, in the course of a week, sunrise might change by half an hour. Because like one day sun might rise at 7:30, then at 7:27, then at 7:21, then at 7:15, then at 7:04, and then it's 6:59 or something like that, right? Like the amount of change that you have on a per day basis is actually pretty great. And that would be the derivative, right? That would be the amount of change, the change in hours based on the day in the year. You end up having the most hourly daylight change per day at this point here, whereas up here at the top of the graph, the peak, or by the way at the bottom, remember this is going to be cyclical, right? In December, on December 21st, then you'll have no change, right? The sunrise and sunset are pretty much stagnant, and they're always at the same time of day. So again, this might not be something that you care about, is how to apply this sort of thing to I don't know what field that is even in, maybe meteorology and the study of weather patterns, maybe predicting sunrise and sunset. You may not care about that, but hopefully you'll agree that it's useful to someone somewhere. So I want to pull it back to this section right here then. The slope of the graph is useful, depending on the context. If you are a farmer who wants to know when sunrise happens to be so we can optimize his watering time for crops, maybe this matters to you. But for everybody else, maybe you don't care. Whereas maybe finding a derivative is useful for ideal gas line chemistry, and you do care about that. So anyways, I'm getting off track here. The slope of the graph could be useful, depending on what the graph happens to be. Finding the slope at any given point could be useful information. So I want to start with a really basic physics example. If a function was displacement over time, the derivative essentially is the velocity. This is something that hopefully you've learned, because all of you should have taken Science 10. If you have a displacement time graph, the slope is the velocity. Usually we don't use d for displacement, though. We usually use s for displacement. I threw it as d right here, but usually we use s, and the biggest reason why is that then you'd have dd, and it gets confusing if d is for a derivative and d is for displacement. But hopefully this is not some new information. Oh, wait, this is the last thing here. Well, what if you took the derivative of a derivative? What if you take the derivative of a velocity? Well, now it's the acceleration, the next graph up of that. If you were to then plot velocity over time, the slope of that graph is the acceleration graph. And so often we need to find a second derivative, which is what I just showed you in last day's video, the d squared over d squared kind of formula, the second derivative. So sometimes the first derivative is important. Sometimes even the second derivative has applications. So I want to do a bunch of examples today. Let's start with physics examples. If I were to give you this graph right here, negative 4.9 t squared minus 12t plus 180, here's a whole bunch of questions we could solve, and we've even done a few of these before. So first question, when will the object hit the ground? Well, we need to consider what we're being asked for here. When the object hits the ground, we're looking for, like, let's just draw a quick little graph here. Here's it's a negative quadratic-y kind of graph. We're looking for when it hits the ground. We're looking for the x-intercept. So to find the x-intercept, that's actually on the original graph. I just need to use the quadratic formula. So if I want to use the quadratic formula to find this x-intercept, I'm just going to go negative 12 plus or minus negative 12 all squared minus 4 minus 4.9, 180 all over negative 4.9 times by 2. And then we just use our calculator to try to calculate the x-intercept basically. Now don't forget there's actually going to be two x-intercepts. Technically there's one for the positive, one for the negative, but one of them is kind of kind of an extraneous root here. I got one of them. I got negative 4.95. I just used my calculator in my hands here, which is probably over here. That doesn't really make any logical sense. So if I try doing it again, though, but I try find the negative version using the quadratic formula, divided by negative 9.8, I got a time value of 7.4. So hopefully you got the same sort of thing here. It's going to take 7.4 seconds for this thing to hit the ground, and that wasn't really calculus, that was just grade 11 quadratics knowledge. So hopefully that made sense, and hopefully I didn't screw up my quadratic formula. Let's try the next one. What is the object's maximum velocity? Well, now we need to do a couple of things we need to consider. First, we need to figure out, well, how do we find a velocity? Well, a velocity is always the derivative of the displacement graph. So the velocity with respect to time is really the derivative of the displacement, which will be negative 9.8 t minus 12. If we find the derivative of this guy right here, constant term derives to nothing. Minus 12 t, its slope is minus 12, and then pull the 2 down in front, minus 4.9 times by 2 is 9.8, which for those of you taking physics, 9.8 should ring a bell because it's gravity. Right. Anyways, going from here, this is our object's, this is an equation for the object's velocity. Now the question is, well, what t value should we plug in? Where will the object have the highest velocity? And this is where kids sometimes they struggle with the word problems because you gotta really be able to think of the context. Right here, there's a velocity, and I could try to calculate its velocity right as it's shot. Right here's another logical spot. At the very, very peak, I could find its velocity there. Or I could find its velocity maybe as it's landing. Well, where's it going to have its most velocity? Well, it's certainly not going to be at the top. Because at the top, doesn't it start to slow down as it gets to the very, very peak and then speeds back up again as it falls? So that doesn't really make sense. The very, very beginning is not a bad thought, but I mean, as I look at this graph here, isn't there going to be more velocity right before it hits the ground because of the way that the physics would work behind it? It's going to be going upwards. Then when it gets right back down to even, it'll have the exact same velocity it was shot with, only in a negative direction rather than positive direction. So that's the whole reason why I wanted you to find this quadratic formula number, is that, and I don't have a ton of room here, but the time value we're going to use is going to be that 7.4 seconds. Because that's when it'll have its maximum velocity. So negative 9.8 times by my answer, and I'm going to use the exact value, by the way, minus 12. I got a velocity of negative 84.597 or so meters per second. And that seems to be where it's going to be going the fastest, is after 7.4 seconds. If I were to try to figure this out after 1 second or 2 seconds, I don't think it's going to be nearly as good as that particular point. So the instant it's about to hit the ground, that would be the fastest. Right. Okay, next one here. I just need to do some erasing. Okay, how long does it take the object to reach a downward velocity of 20 meters per second? Well, I have a formula here that gives you a velocity. So I want it to eventually equal negative 20 meters per second. It starts off like this. So let's calculate when it eventually equals 20. Add 12 to both sides, means that minus 8 equals minus 9.8 t. Divide by 9.8, divide by minus 9.8. My time value is 8 over 9.8, which is about 0.816 seconds, give or take. By the way, I should point out, I don't actually care about sig digs here. Unlike the physics formulas, I just want you to, I mean, the best answer, honestly, is actually 8 over 9.8 seconds. That's probably the best answer. But if you need to round it, I don't really care what you round it to. So, okay, another example here. What is the velocity of the object when t equals 2 seconds? Well, again, your velocity is equal to negative 9.8 times your time minus 12. So if the time is 2 seconds, I'll just plug in 2 seconds. Negative 9.8 times 2 minus 12. Minus 31.6. Seems to make sense. Well, not seconds. That's meters per second. It's still not the smallest velocity we have. Remember, this one over here I wrote down was about negative 84.5, so it's not as much as it could be. After 2 seconds, it's only 31.6. After my 7 seconds, we're up to 84.5. So, okay, last little bit here. Let's find the acceleration. Well, the double prime for displacement is the same as the prime for velocity is the same thing as the acceleration graph. So I just need to take the derivative again. How do you find the derivative of this guy right here? Well, it's just negative 9.8. Which I actually threw this on your midterm, by the way. I put this question on there. Find the derivative of the derivative. And this makes all the sense in the world because what is the acceleration always on Earth? Negative 9.81. So, okay, I blitzed through those ones pretty quickly. If I lost you on kind of the reasoning behind what I did, please make sure you let me know or rewind the video. The thing I need you to be aware of is that the work behind this, the actual calculus, is very basic. You don't do a lot of derivatives, but what you're usually doing is you're finding a derivative and then plugging in 2, or finding a derivative and seeing where it equals 20, or finding a derivative and then plugging in some sort of other value which was based on a previous number. So there's a good physics example. Now, again, one of the goals I had today was to show you the appreciation of that this matters to someone somewhere. So one of the things we may need to do then is try to figure this out in, like, say, a biology context. So the idea behind this concept here is that you've got some bacteria, and the bacteria is growing according to this function. And it's not exponential, but it's growing slowly but surely over time. This particular function right here, I could even say, like, the initial amount of bacteria is going to be 500, right? Because as the time begins, this is how much bacteria you have. But slowly over time, your bacteria seems to be multiplying greater and greater and greater. So I want to find the rate of growth after 5 hours. I don't actually want you to tell me how many bacteria I have. I want you to tell me how fast they're growing. Let me see if I can make sure it's clear on this. If you're just to plug in 5, this value right here just tells you how many bacteria you have. So I'm going to do 12 times 5 squared plus 200 times 5 plus 500. At this point here, you'd have 1,800 bacteria. But that's not what I'm asking you for. I'm not asking you for how many bacteria you have. I want you to tell me how fast they're growing at this point here. Let me give you a couple of different examples here. What if I did N4, and I did N3, and I did N2, and I did N1, and I did N0, just to make a point. So I'm just going to solve some values here. Hopefully you can do the exact same thing in my calculator, or in your calculators. We started with 500 when we began. And then if we were to do N1, 12 times 1 squared plus 200 times 1 plus 500, after 1 hour, you'd have had 712 bacteria, which means that you'd have grown by 212 bacteria per hour. Okay, well, let's try to find the next number here. So let's try to plug in 2. So if after 2 hours, how many bacteria would you have after 2 hours? And you guys can slow down and pause the video if you need to, but I got 948, which means that from hour 1 to hour 2, you're up to 236 bacteria being grown in the hour. And hopefully you'd agree, well, our growth rate is increasing, isn't it? Like we're increasing how much growth we have. You used to go up by 212, now you went up by 236, right? So if we keep extrapolating that up to, like, say, N4, I'm going to throw in 4 now. In hour 4, you'd have had 1,492 bacteria. Well, in hour 5, you had 1,800, which means that you are actually going up by 308 bacteria per hour. So hopefully you can kind of see that from hour 4 to hour 5, you were increasing by 308 bacteria per hour, but I mean, that's actually still doing things in large block increments. I like to find the exact growth rate at hour 5, because this is really the growth rate from hour 4 to hour 5. By hour 5, you're probably not at 308 anymore. We're probably even higher than that. Right? You can kind of imagine what I'm saying. This is like the whole idea of that whole, when you make your graph, and you want to make that h getting closer and closer to 0 as you bring that point in from, like, say, P and Q. You want to bring it closer and closer, make the limit equal to 0. We found what happened between 4 and 5, but I want to find the instantaneous growth rate at 5, not just kind of the slope between the 4 and 5. So here's how we solve this. Now that I've kind of done a whole bunch of non-essential work in our preamble, we want to find out how fast are the bacteria actually growing in hour 5. Not how many bacteria do we have, but how fast are they growing? So we do this. The derivative would be 24t plus 200. This is your growth rate. This is how fast they're growing. Now we can plug in 5 hours. And here's what we get. 24 times 5 plus 200 means that we're actually growing at that point at 320 bacteria per hour, which kind of makes sense because when I was doing those numbers, I just finished getting 308. Right? It was from hour 4 to hour 5. Our growth rate was 308 bacteria per hour. But the bacteria growth doesn't just happen on the hour mark, right? It's always constantly happening. So it makes sense that at hour 5, it's already growing even faster than that. And at hour 6, it's going to be even further than that too. So anyways, here's an application of how we can use that in the biologies. And I mean, the math was drop dead simple. We took a derivative, we plugged 5 in. That's all there was to it. But the harder part is, can you wrap your head around the context in which this has to occur? So, okay, here's an example in the economics field. C is the cost for a business to produce items, and this is an economics term here. It's known as the marginal cost. It's the change in cost per change in items. Let's see if I can make sense out of this with these next lines here. Let's say that you're a business and you make, I don't know, toys. If you make one toy, the amount of cost that it has is going to be pretty high. But the price per item is going to be higher the more that you produce. The more items you produced, the more it's going to cost you to produce. However, the price per item should decrease. Right? Like, let's say that I make one toy. I might have to charge $10. But let's say that I make 100 toys. I might be able to get away with selling them only for $90 rather than 100, because the price per item can go down as you make more of them, right? That's the whole idea of economy of scale. Maybe even notice this if you go to the grocery store. If I were to buy onions and I buy like a 1-pound bag of onions, it's nowhere as good of a deal if I buy a 3-pound bag of onions. And I get an even better deal if I buy a 10-pound or a 20-pound bag of onions. The more you buy, the cheaper it is. So the marginal cost then is the change in cost per item. Basically, the idea is, how much does it cost to make the next bag? If I'm making item 1 to item 2, how much does it cost? Whereas if I'm making item 1 million to item 1,000,001, how much more does it cost? And usually at a certain point, the amount that it costs to make the next item goes down the more you make. That's just that. Hopefully that makes intuitive sense. The more you make, the cheaper they get. Usually because your overhead costs are already paid for. So I'm doing this example for the second time here. I'm actually snipping this video in with the previous one because I made a typo in the example, and so I need to fix that. So there's a 2 up here as an exponent that should have been a 1/2, and that drastically changed this question. So it needs to be 5,000 plus 3x plus 0.02 root x. That's the equation we need. And so I'm snipping this last example in with the previous stuff I worked on. So I just need to remind myself a little bit, as well as recap what we were working on. In economics, the concept is the marginal cost. And marginal cost is how much it costs to make, like, say, the next item. So you're looking for the change in cost per items. You're looking for how much does it cost to make, say, 100 versus 101 items, which is what we're going to do in this example here. So to start with, I'm just going to find how much it costs to make 100 items. So to make 100 items, take 5,000, add 3 times 100, and then to that add 0.02 times the root of 100, and solve that. And then if you do, you end up getting $5,300.20, which is basically how much it costs for you to make your 100 items. So if you want to figure out the price per item, then you could just divide that by 100, and then dividing that by the 100 items means that it basically costs $53.002. So basically $53 an item to make 100 items. So, well, now I want to do the exact same thing, but with 101 items. So I'm kind of running out of room here. I'll do another color. I'll go below here. You use the exact same equation, only now use the number 101 rather than 100. So same equation, but now 101. And if I do that, 5,000 plus 3 times 101 plus 0.02 root 101, it ends up being slightly more. Now, we're not talking a lot more, but just slightly more. 5303.20, but then if I kind of keep going, it's 200,998. And hopefully you'd agree that, I mean, the amount that it costs goes up. But really, once you've made 100 items, producing the 101st item it barely costs anything more, right? The difference between the two is essentially this amount right here. It's very, very low. That's quite small. That's essentially the marginal cost. This right here is how much it costs to make the next item. So one way we can calculate that is to essentially to find the 100th item and the 101st item and subtract. But another way of doing it is to find the derivative. And so the derivative is going to be, if the original function is 5,000 plus 3x plus 0.02x to the 1/2, to find the derivative, it would look like this. Derive 5,000, it derives to 0. Derive 3x, it derives to 3. And then when you want to derive this guy right here, you have your 0.02, pull down the 1/2, and make x go to the minus 1/2. This would be your equation. I'm going to simplify this a little bit right here. 0.02 divided by 1/2, or yeah, divided by 2 basically, just timesing by 1/2, makes it 0.01. So here's my derivative. The derivative is 3 plus 0.01 x to the minus 1/2. Well, this is another way to find your marginal cost. If I want to find out the marginal cost for my 100th item, I'm just going to plug 100 into this equation. So 3 plus 0.01, 100 to the minus 1/2. This is a more efficient way of finding your marginal cost. And I ended up getting 3.001. I realize right now that I actually made a mistake when I was showing you this first example here. This right here was $5,300, and this right here is $5,303, which I think this makes sense, right? Because the difference between 5,303.200998 subtract 5,303.20, the difference between that, 5,300, would be $3. And I mean, basically this guy right here, if you want to round it, I guess I can see why there's an 01 there. Hopefully you guys can kind of see how this works in this example here, is that the difference between the 100th item and the 101st item, the difference between the two is about $3. So that means that to make your 100th item to your 101st item, $3 more, right? I mean, that's why the economies of scale are so good for you to buy things in bulk, because really your overhead costs have already been covered. The overhead cost in this example, by the way, is $5,000. That's kind of like your overhead. If you ever heard of that before in economics, that's how much you need to pay regardless. If no one purchases anything, you still got to pay $5,000. Right? That's your cost regardless. And then based on the item, that's where X comes in. So, I mean, your price per item when you had 100 items was basically $53 an item. If you wanted to right here, I didn't ask you to do it, but if you wanted to divide this by 101, the 5,303 divided by 101 would actually give you a price per item of $52.51. So, I mean, in this example right here, if you make 100 items, it's $53 an item. If you make 101 items, it's actually only $52.50 per item. So it gets cheaper per item as you go along. Anyways, the marginal cost, though, is how much more it costs to produce the next item. That's a marginal cost. So we can find that using a derivative. Well, the marginal cost should decrease as you make more items as well. If you have an equation that's valid, the marginal cost should be decreasing as you go along. And I hope that actually is discovered as you do the 500 items example right here. So I want to try that one more time here. Let's find the marginal cost for 500 items. The marginal cost for 500 items is now going to be 3 plus 0.01, 500 to the minus 1/2. And if this is actually an equation that's been made properly, then we should discover that it should cost less the more items you make, right? Yeah, this time around I ended up getting 3.00044714. So to make the next item from the 500 to the 501st item, it still costs basically $3, but here it was $3.001. Now it's $3.0004. So hopefully you can see that the amount it costs to make the next item is going down. So that's why the per item basis is decreasing. So anyways, to summarize, that's basically what's happening when you're working with economics, is if you want to find the derivative of cost with relation to items, that is how much it costs to make the next item. Okay, that's the end of this particular lesson. I'll snip and I'll merge my two videos together. What we're going to do next day is we're going to talk about some more equations on rates of change, and this is going to kind of continue our section on the word problem section. So if you want to look ahead at our notes here, pretty much all of our examples in the next section are going to be word problems. They may not necessarily be specific to either economics or to biology or physics or chemistry, but usually there's a lot of overlap in these fields. So, okay, that's the end of my video.